Okay, so this is a video that has kind of two parts. The first part is on symbolic logic, and the second part is on algebraic proof. Okay, so we're looking at symbolic logic. Okay, so this is using symbols to represent logical argumentation. The basic idea is that if you have a conditional statement, which is something in the form of if P let's try that again. If P, then Q. Okay, so symbolically we write this as P arrow Q. So that's the basic conditional statement. If something, then something else. Okay, we've seen one way to do an opposite of this, which is what we call a converse. So if you remember, the converse is a statement in the form if Q, then P. So that can be written as Q arrow P. So we switch the if and then parts. Now recall that the truth value of the conditional and the converse are independent of each other. So the conditional can be true and the converse could be either true or false. We have a thing called an inverse, which is another way of doing an opposite. And in this case, we just negate both parts. So we say if not P, then not Q. So this would be like if our original statement was if today is Tuesday, then tomorrow is Wednesday. Then the inverse would be if today is not Tuesday, then tomorrow is not Wednesday. So you can write this as not P implies not Q. So that little arrow there is not P to not Q. Again, the inverse is like the converse. It has no relationship to the truth value of the conditional. So the inverse can have a very different truth value. So the conditional could be true, and the inverse can be true or false. Finally, we get something called a contrapositive. And in a contrapositive, you both switch the P and the Q, and you negate both. So this would be if not Q, then not P. So you can write this symbolically as not Q goes to not P. Now here's the interesting fact. If the conditional is true, then the contrapositive must also be true. If the conditional is false, the contrapositive will also be false. So let's take a true conditional where the converse and inverse are not true. So the example that we used earlier was that if I am a garrison for a student, then I am a student of an independent private school. That's a true statement. The converse says that if I'm a student at an independent private school, then I'm a garrison for a student. That would be false. Because like a student at McDonough or a student, say, Roland Park Country School are students at independent private schools that are not students at Garrison Forest. Okay, the inverse would also be false in this case. If I am not a Garrison Forest student, then I am not a student at an independent private school. Well, again, a McDonough student is not a Garrison Forest student, but they are a student in an independent private school. So the inverse and converse clearly don't have to have the same truth value as the conditional. However, use that example with the contrapositive. If I am not a student at an independent private school, then I am not a Garrison Forest student. Aha! Well, that's true. See, the conditional and the contrapositive must have the same truth values. Okay, so let's look at these two. Note, with the converse and the inverse, you are switching Q, P, and you are making negative. So the inverse is actually the contrapositive of the converse, which means that these two have to have the same truth value. So if the converse is true, the inverse must be true. If the conditional is true, the contrapositive must be true. So you have things that come together in the same logic. And this is the symbolic representation of that. Okay, so we can construct something that is called a truth table. And in my truth table, I'm going to have a column for the P, a column for the Q, a column for the conditional statement, a column for the converse. I'm going to have a column for the inverse, and a column for the contrapositive. Okay, so P, Q, we've got everything we need here. Okay, so what we do is we build these columns, right? And then we figure out what are the possible values for P and Q. Okay, so there's 2, 3, 4 possible values here. Okay, so P can be true and Q true, or P true and Q false, P false and true, P false and false. So if a conditional is true, when the hypothesis is true, the conclusion must be true. So I get true when I have T, T. True. But if the hypothesis is true and the conclusion is false, then the whole thing is false. Okay, so let's look at this situation. This is where things get a little bit illogical. If the hypothesis is false, none of the rest of this matters. So if the hypothesis is false, the statement is true. Okay, so this is a bit of a strange reality here. If you think about this, if pigs can fly, then I'm a millionaire. Well, pigs can't fly, so it doesn't matter whether or not I'm a millionaire. The statement is still true because I don't know what could possibly happen if pigs could fly. So, yep, I hold those statements as true until I can get a counterexample and disprove them. I'm not going to get a counterexample of flying pigs, so I'm going to hold them as true unless I have a counterexample. So this is the basic idea. True, true gets me true. True, false gets me false. False, true gets me true. False, false gets me true. Now, with the converse, I'm switching the Q and the P. So the Q becomes the first value. The P becomes the second value. So this is going to be true, true gets me true. False, true. So since I started with false, I've got pigs flying. That's true. True leads to false, makes my table false there. And false, false, starting with pigs flying, gets me true. So note, this is the truth table for the conditional, and this is the converse. Note the two tables are not the same. They're independent of each other. Alright, so let's try the inverse. Okay, so not P would be false. Well, anytime the hypothesis is false, I'm true. Okay, same thing here. Not P would be false, so that's true. Okay, not P this time would be true. True, true makes, true, false, right? Because this is not Q. So true, false makes this false. And not P is true, not Q is true. True, true makes this true. Note, 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 very important. The converse and the inverse have identical truth values, which means that this is true whenever this is true. These two have the same truth values. Okay, so let's try the contrapositive. Not Q would be false, so that makes the whole thing true. Not Q would be true. Not P would be false. True to false makes it false. Not Q is false, so the whole thing has to be true. not Q is true, not P is true, true, true makes it true. Okay, so note, here, the statement, the conditional statement, and the contrapositive are both true, true, or true, false, true, 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 false, true, true. So whenever the original statement is true, the contrapositive must also be true. Okay, so now we're going to take on a second topic in this video that is somewhat unrelated. This is on algebraic. So that's just the word algebra proof. Okay, so we're going to do proofs involving algebra. This is geometry. Yeah, we're going to learn from algebra first. All right, so first thing we need is that there are some key properties of equality. Okay, and we get 3 of these. One is called a reflexive property. One is called a symmetric property. And one is called the transitive property. Okay, the reflexive property is pretty simple. So if you think reflection, reflexive, that kind of deal, the reflexive property just says that every number is equal to itself. Pretty simple, pretty straightforward. The second property, the symmetric property, says if A equals B, then B has to equal A, which means that you can switch things with respect to an equal sign. So you have symmetry over the equal sign. The transitive property says if A is equal to B and B is equal to C, then we can conclude that A is equal to C. Okay, so if A is equal to B and B is equal to C, then these things are equal to each other. Okay, so that's how we deal with properties with respect to equality. We also have a set of properties of algebra. Okay, so number 1 is what we call the addition property. Addition property just says that if A is equal to B and C is equal to D, then we conclude that A plus C is equal to B plus D, which is basically saying we can add equal values to both sides of the equation and not change whether or not the equation is true, which is something that we commonly do in algebra. Okay, so like an addition property, we have a subtraction property, which says that if A is equal to B and C is equal to D, then like we can add the same value to both sides, we can also subtract the same value from both sides. So we can take 2 things that are equal, subtract them from both sides of the equation. Note, we have a multiplication property. Big surprise here, that if A is equal to B, then C times A is equal to C times B. So if you multiply both sides of the equation by the same number, then the truth value of the equation doesn't change. The division property. Okay, so there's a small caveat here. If A is equal to B and C does not equal to, D, no that's not right. C does not equal Z, then we can say that A over C is equal to B over C. So to remember, C cannot equal to 0, because you cannot divide by 0. That's illegal. If you try to divide by 0, the world will blow up. Alright, so division works so long as what I'm dividing by on both sides is not 0. Okay, so we have another property called substitution, which I think we saw a little bit earlier this year. But substitution says that if A is equal to B, then you can replace A with B in any equation, wow, that's getting ugly, there we go, equation, or inequality. Okay, finally we have a distributive property, which tells us that if I take A times B plus C, this is the same as AB plus AC. Okay, so these are the major properties of algebra that we start off with in this course. Now the question is like, why do we need these? Okay, so let's do an algebraic proof. Okay, so here's an example. Okay, we're going to be given a certain piece of information. We're going to be given an equation. We're going to be given that 3x is equal to 6 minus 1/2 x. And I want to prove this. I want to prove that x is equal to 12 over 7 is its solution. So I already know the answer. I have to show that that's the case. So what we do is we put a little table here. And we create on one side a table for statements. And we create on the other side a column for reasons. So what's careful about geometry is not so much that we know the answer, but it knows why we got from here to here. How do I make a set of logical steps that get me from one place to the other? So let's say I have 3x is equal to 6 minus 1/2 x. How do I know that? Well, it was given to me. This is what I started with. So I put in there as my reason that this was given information. Okay, so a logical first move here may be to actually get rid of this fraction by multiplying through everything by 2. So if I multiply the left by 2, I get 6x. If I multiply the right by 2, I get 12 minus x. What did I do? Multiplied both sides by 2. So this was done by the multiplication property, which says if I multiply both sides of an equation, I get an equation that's true for the same values. Okay, so I think my next move here would be to add x to both sides. So if I add x to the left, I'm going to get 7x. If I add x to the right, I get 12. I added something to both sides. So this is the addition property. And then typically at this point, I would divide both sides by 7. Well, what did I do? I divided both sides by some non-zero number. That is the division property. And I'm done. I've proven that this given leads inextricably to that prove statement. And this is the steps that I would use. And these are the reasons that I can use those steps. So this is a proof of an algebraic construct. So it's an algebraic proof. So summarizing what we've talked about during this, you can build a truth table for conditional statements. If P, then Q, right? Their converses. If Q, then P. The inverses, not P, then not Q. And the contrapositives, not Q, then not P. And we've shown that the statement and the contrapositive have to have the same truth value. The inverse and the converse, so this one's the inverse, this one's the converse, have to have the same truth value. Okay, the other thing that we did is we discussed a series of properties of equality, reflexive, symmetric, and transitive, and a series of properties of algebra, addition, subtraction, multiplication, division, substitution, and a distributive property, distribution. And then we used some of these properties of equality and algebra to show the why. Why can I do something when I'm solving an algebraic equation? And we called that algebraic proof. Proof. We've actually proven something. All right, so thank you.